Good evening, and welcome to Story of the Cosmos. Tonight, we travel toward a single red point of light, so large that the mind struggles to hold its true shape. Somewhere in the constellation Scutum, low toward the crowded heart of our galaxy, there is a star that has not yet been named, a faint, reddish smudge, barely a whisper against a sky already thick with dust. From here, it looks like nothing at all, one more point among thousands, unremarkable to any eye scanning the dark. But look longer. Let the eye settle where the light gathers and dims, in that dense stretch of sky where the galaxy's spiral arm folds in toward its ancient bar. There is nothing sudden about this place. No burst, no flare, only a slow red glow held very still, as if waiting. It has waited a long time already. The light reaching us tonight left that star thousands of years ago, crossing the galaxy in silence long before it ever touched a telescope, long before anyone thought to look for it at all. We are not ready yet to give this point of light its name, or its staggering size, or the strange, unsettled questions about where it truly belongs. For now, it is only this: a quiet red ember tucked into a corner of Scutum, patient and unnamed. Let it simply sit there a while, in the dark, before we come closer. Consider for a moment how easy it would be to miss almost everything out here. Astronomers estimate our galaxy alone holds something like 200 billion stars. Some counts run higher, toward 400 billion, because even our own neighborhood is too vast and too dust-choked to count exactly. That is more stars than there are grains of sand on every beach on Earth, all of them turning slowly inside one ordinary spiral galaxy, one among perhaps 2 trillion others scattered through the visible universe. Stand outside on the clearest, darkest night you can find, far from any city glow, and you might see perhaps 3,000 of them with your bare eyes. 3,000 out of 200 billion. Everything else, the vast, overwhelming majority of the stars in the Milky Way, burns too faint, too distant, or too buried behind interstellar dust for human eyes ever to register at all. So when astronomers speak of the largest known star, they are not describing the largest star in the universe. They cannot know that, not yet, perhaps not ever. They are describing only the largest star that anyone has managed to notice, measure, and argue over. A title drawn from a search that has barely scratched the surface of a galaxy where most of the residents remain, in the truest sense, strangers to us. And size does not announce itself the way you might expect. A star swollen far larger than our Sun can glow cool and dim, almost sullen, while a much smaller star nearby burns hot and brilliant. The biggest objects are often not the brightest ones. They can sit for decades, even centuries, hiding in plain sight, simply because no one thought to look closely enough, or in the right kind of light. That is what makes a title like Largest Known Star so fragile. It is not carved into anything permanent. It shifts every time a telescope sharpens, every time a distance is remeasured, every time dust that once concealed a star thins, even slightly, from our line of sight. Whoever holds the record tonight may not hold it in 10 years. Not because any star grew or shrank in that time, but because we are still only beginning to adjust our instruments and our eyes to the true scale of what surrounds us. Hold on to that uncertainty. It belongs to the star we are about to meet. A fragile crown, worn quietly in the dark. In 1990, an astronomer found tens of thousands of suns hiding behind a wall of dust. He was not looking for stars in the usual way. Charles Bruce Stephenson was scanning the sky in infrared light, the kind of light that slips through dust the way a flashlight beam slips through fog, when ordinary starlight cannot get through at all. And there, low in the constellation Scutum, toward the crowded heart of the galaxy, he found something that had been sitting in plain sight the entire time, and had simply never been seen. It was a cluster. Not a handful of stars, but an entire stellar nursery, its combined mass estimated at something like 40,000 times the mass of our Sun, one of the most massive young star clusters ever found in the Milky Way. It sits at a very particular address, the point where the Scutum crux spiral arm, one of the great pinwheeling structures of our galaxy, meets the dense bar of stars and gas running through the galactic center. A crossroads. And crossroads, in a galaxy, tend to be crowded. A cluster this massive, this dense with dying giants, cannot be old. The stars that make it what it is burn far too fast and far too briefly for that, which means this whole gathering, dust and all, is thought to be only 10 to 20 million years old, a flicker of a flicker by the galaxy's own reckoning. That crowding is exactly why no one had noticed it before. Along this line of sight, dust and gas pile up so thickly between us and the cluster that ordinary visible light is almost entirely swallowed before it ever reaches Earth. Only the longer wavelengths of infrared survive that journey. Patient, low-energy light, carrying its message through a wall nothing else could pass. Careful study later confirmed 26 red supergiants, stars nearing the ends of their lives, swollen and glowing, as true members of this hidden cluster, drifting through space together at nearly the same speed, bound by the same gravity, born together in the same single burst of star formation. Wider searches around its edges turned up roughly 80 more candidates, stars sharing that same quiet drift, suggesting that what Stephenson had found was only the dense core of something larger still, an association that may scatter hundreds of red supergiants along this single arm of the galaxy. Together with a neighboring cluster, found separately in the same crowded region, this hidden gathering would turn out to hold roughly a fifth of every red supergiant then known in the whole Milky Way. A fifth of a galaxy's dying giants, tucked behind dust, unnoticed until someone thought to look in a color of light the human eye was never built to see. One of its stars was still unnamed. Stephenson 2 and its newfound neighbor held, between them, a fifth of the galaxy's dying giants, and one of Stephenson 2's stars was still unnamed. That star would eventually carry a number instead of a myth. Stephenson 218. There is nothing dramatic about the name. No hero, no hunter, no god. Just a catalogue entry, DFK1, folded into a survey list, and yet the object behind that label is almost too large to hold in the mind. Its radius, by the best current estimate, reaches something like 2,150 times the radius of the Sun. Not 2,150 times brighter, times wider. Picture the Sun first, small and white-hot and finite, a single point holding its planets in a tight, ordered loop. Now let it swell, not violently, but slowly, over hundreds of thousands of years, expanding past every scale that once described it, until the star that results could not be mistaken for anything like our own. And as it grew, it cooled. That is the part easy to miss. Bigger does not mean hotter. Stephenson 218's outer surface, spread across that enormous volume, has cooled to somewhere near 3,200 Kelvin, barely half the Sun's surface temperature. A star that size, burning at that temperature, does not shine white or blue. It glows a deep, banked red, the color of embers rather than flame, dim compared to hotter stars its size would suggest, patient in a way starlight rarely is. Try to hold both numbers in mind at once. 2,150 suns wide, and yet only 3,200 Kelvin at the skin. It is less a star that burns fiercely, and more a star that has spread itself thin, its warmth stretched over so vast a surface that little of it reaches the eye as bright light at all. Astronomers reading its glow find the color of a coal at the bottom of a dying fire, and yet, summed across a surface that would swallow Saturn's orbit, that ember light adds up to hundreds of thousands of suns worth of shine, most of it pouring out as infrared warmth no human eye can see. A coal, but a coal the size of a solar system. There is no photograph of this. No telescope has resolved its face into a disk the way an eye resolves a coin from across a room. What astronomers have is light, its brightness gathered across every wavelength, its color measured precisely enough to infer a temperature, and from those two threads alone, a size is calculated rather than seen. It is worth remembering, quietly, that a number this large rests on an inference, not a photograph. Still, red is the color it would show if a human eye could survive close enough to look. Not a point of light anymore, but something closer to a low red horizon, filling half the sky. A star once unnamed, now the largest ever measured, glowing the color of dying coals. Stephenson 2-18 has already grown vast in the listener's mind. Now the segment needs to ground that in orbital distance. Let me write it. The star's surface, if it burned where our own sun does, would not stop at Mars. It would not stop at Jupiter either. Set Stephenson 2-18 down at the center of our solar system, in place of the Sun, and its edge would sweep outward for nearly 10 astronomical units in every direction. Each of those units itself the full distance from Earth to the Sun. Mercury would vanish first, swallowed almost instantly, its tight little orbit lost somewhere deep inside the star's outer layers. Venus would follow, then Earth, and everything on it. Mars, the last of the small rocky worlds, the one so often imagined as a future home, would already be gone, folded into the star's slow-moving atmosphere long before its surface was reached. The star would keep going. Jupiter's orbit, that wide, patient circle that takes nearly 12 years to complete, would lie inside the star as well. So would the space where the asteroid belt drifts. And so, very nearly, would the orbit of Saturn, that soft, ringed world often used as the edge of the inner solar system in the imagination. Stephenson 2-18's measured diameter comes out to almost 20 astronomical units. Put simply, a star that large, sitting where the Sun sits, would reach out far enough to brush against the realm of the rings. It helps to have something nearer to compare it to. Betelgeuse, the familiar red shoulder of Orion, is itself enormous. In the Sun's place, it would swallow Mercury, Venus, Earth, and Mars. Though even Betelgeuse, our best-studied red supergiant, keeps having its size revised as instruments sharpen. Betelgeuse is only a few hundred light-years away, close enough to be watched, studied, argued over in exquisite detail. Stephenson 2-18, if its measurement holds, is wider still, perhaps half again as wide, perhaps more, and it sits more than 30 times farther from Earth than Betelgeuse does. There is no photograph of this. No telescope has ever resolved a disk of Stephenson 2-18 the way a coin might be seen from across a room. What exists instead is a number, built carefully from light and temperature and distance. A number large enough that, if it is even close to correct, a star could stand in for our entire familiar solar system and still have room left at its edges for the rings of Saturn to glow faintly through its outer haze. 10 astronomical units in every direction, and then nothing but the star. 10 astronomical units in every direction, and then nothing but the star. But that number was never a photograph. No telescope has ever resolved a disk of Stephenson 218 the way you might resolve the face of a coin held up to the light. What astronomers have is something quieter and more indirect. A measured brightness, a measured color, a temperature read from the tilt of its spectrum. From those two numbers alone, brightness and temperature, a simple law from 19th century physics lets you work backward to a size. Not a ruler laid against the star, an inference built on light that has traveled 18,900 years to reach a detector on Earth. And because it is an inference, it moves when the inputs move. Change the assumed distance to the star, even slightly, and the luminosity changes with it, and the radius changes with that. This is not a flaw unique to Stephenson 218. It is the condition every claim of largest known star has always lived under, which is why the title has never stayed still. For a long while it belonged to VY Canis Majoris, then to UY Scuti, whose radius was once put near 1,700 times the Sun's, until better distance measurements from a newer generation of space telescopes pulled that estimate down towards something closer to 800. More recently, the red supergiant WOH-G64, far across the sky in a neighboring galaxy, was finally caught in a direct image in 2024, the first close-up portrait of a star beyond the Milky Way, wrapped in its own egg-shaped shroud of dust. Even that resolved image left its size uncertain, swinging between estimates as different methods disagreed. Stephenson 218 now carries the title by the same fragile arithmetic. Its radius, some 2,150 suns, is the best current answer to a question that keeps getting re-asked as instruments improve. And it sits at the edge of what current models think a red supergiant's outer layers can even hold together before growing unstable. Some astronomers suspect the true figure is smaller. None of this makes the star smaller in importance. It only means the record book is written in pencil, not ink. Each entry waiting for the next parallax measurement, the next dust model, the next distance revised by a few percent to rewrite the ranking entirely. The largest star we know of is only the largest star we've managed to measure. Every star in Stephenson 2 was counted, one, by matching its motion to its neighbours, all except one. Stephenson 218 sits at the outer edge of the cluster that carries its name, and when astronomers measured how fast it moves along our line of sight, the number didn't quite match. The 24 or so red supergiants, confirmed as true members of Stephenson 2, drift together, bound by the same gravity, born in the same burst of star formation, moving as a family through the galaxy's disk. This star drifts slightly differently. Not by much. Just enough that some who have studied it are no longer willing to call it a member at all. Enough that one analysis described it plainly as a field red supergiant, a wanderer that happens to sit along the same crowded sightline as the cluster, rather than a true resident of it. A study in 2010 tried to give that ambiguity a home of its own. Placing the star in a separate, more loosely scattered subgroup, it named Stephenson 2 Southwest, presumed, for now, to sit at roughly the same distance, but treated as its own small population rather than folded into the main cluster. It's from that reassignment that the star picked up the number 18, the label that has followed it ever since, into headlines about the largest star ever found. So the record holder may not, strictly, live where its own name says it lives. Nothing about the light reaching us tonight can fully settle the question. The same dust that hides the whole region from ordinary telescopes also blurs the fine motions astronomers would need to measure to know for certain. Is it a founding member of one of the most massive young clusters in the galaxy, or only a stranger passing near enough for a little while to be mistaken for family? It may be both possibilities at once, unresolved, for as long as anyone keeps watching. A record can be true and its address still unknown. 10 million years is nothing to a star like the Sun, but for something this heavy, it may already be almost enough. Stephenson 2.18 did not begin its life red or swollen or strange. Like the other giants scattered through its crowded corner of the galaxy, it was born blue, a hot, blue-white star of perhaps 10 to 40 times the Sun's mass, burning through its hydrogen at a furious, unsustainable rate. That blue youth lasted millions of years, which sounds long, until you remember that stars this massive are always living on borrowed time. Then the hydrogen at the core ran out. The core contracted, heated, and helium fusion lit in its place, and the star began to swell, not gradually, but by hundreds of times its original size, cooling as it grew, sliding down the spectrum from blue toward white, then orange, then the deep, banked red we see today. This is the red supergiant phase. It is brief, a few 100,000 years, perhaps close to 1 million, a short, unstable coda after a much longer, quieter youth. Inside, the fusion never really stops. It only moves to heavier fuel. Helium into carbon, carbon into neon and oxygen, oxygen into silicon, each stage burning faster than the one before it, a countdown that compresses toward its final days as it climbs the periodic table. Eventually, what's left at the center is a core of iron, and iron cannot give the star any more energy by fusing further. There is nowhere left to go. When that moment comes, the iron core collapses in a fraction of a second, and the star tears itself apart in a core collapse supernova bright enough to briefly outshine every other star in its home galaxy combined. What remains of the core crushes down into a neutron star, or, if the star was massive enough, a black hole. Everything above that core is hurled outward into the surrounding dust and gas, carrying carbon, oxygen, and iron with it. The raw material, eventually, for new planets, new stars, perhaps new life, forged in a death no one is left to see up close. Astronomers have noticed something odd, though. Fewer of the very brightest red supergiants turn up as confirmed supernovae than the numbers predict. A puzzle some call the red supergiant problem. One quiet possibility is that the most massive of these stars never flash at all, that some of them collapse straight into a black hole, taking their light down with them, ending not with a blaze, but with a silence. Stephenson 2.18's own ending, on this scale, is already close. It does not stand alone. Around Stephenson 2.18, in the same crowded field, 26 other red supergiants have been confirmed sharing this stretch of sky, the largest gathering of its kind ever found in the galaxy, born from an initial cluster mass of some 40,000 suns. Survey after survey has since turned up dozens more candidates, scattered along the same spiral arm, suggesting the cluster we can name is only the dense heart of something far larger, still mostly uncounted. Among these neighbours sits a quieter giant, Stephenson 2 DFK 52, fainter than Stephenson 2.18, easy to overlook beside it, And yet, in 2025, astronomers found DFK 52 wrapped in the largest shell of shed material ever documented around any supergiant, a cloud of dust and gas spanning some 50,000 astronomical units, 3 to 4 times wider than the already enormous outflow around VY Canis Majoris. The shape of that cloud tells of one violent event, a sudden ejection some 4,000 years ago, after which the star seemed to settle back into calmer, steady mass loss. No model of a single aging star fully explains why, nor why Stephenson 218 itself may not truly belong to the cluster bearing its name. This crowded, dust-choked corner of the galaxy keeps producing questions faster than astronomers can answer them. Even among giants, some things stay unaccountable. Whatever Stephenson 218 looks like at this exact moment, no one will know for millennia. What reaches us is an old signal, still arriving, still telling the same slow story it started telling before the last ice age ended. And in all that time, the star hasn't hurried. It sheds roughly a sun's worth of itself every 74,000 years, breathing slowly into the dust around it, unconcerned with whether anyone ever agrees on its size, its distance, or even whether it belongs to the cluster carrying its name. The swollen, red final stage a massive star enters usually lasts only a few 100,000 years, and Stephenson 218 may already be deep into that chapter. How much of it remains, no one can say. The ending could be hundreds of thousands of years away, or far closer than anyone suspects. What is certain is only this. Tonight, the glow is still there, burning quietly in a corner of the galaxy no unaided eye will ever resolve. Somewhere far ahead, its core will finally give out, and it will end the way stars like it end, briefly, violently, then dark, scattering itself into the raw material of worlds not yet made. But that is not tonight. Tonight it is simply there, doing what it has always done, indifferent to the hour, indifferent to sleep. It was burning before you closed your eyes tonight. It will be burning tomorrow, and the night after that, and for a very long time beyond any of your nights. Somewhere in Scutum, that faint red point is still sitting exactly where it has always been. It doesn't need you awake to keep shining. This has been a story of the cosmos. Out there, the stories go on, slowly, quietly, as they always have. Let this one drift on without you, until the next journey.